Hi, in this video, I'm going to talk about support force and also vector decomposition. So let's just get into the notebook here. Okay. So support force, normal force, the same thing. Support force, normal force. Support force, normal force. As I mentioned, solid materials are made of a bunch of molecules and atoms, and they're bounded tightly together. And then how they're tied is you can imagine that they're almost like connected with the tiny little springs. So on the solid surface, it's like this. You have a bunch of molecules and atoms that's tied, and they're bounded tightly with the springs. Solid object. And when you touch the surface of such an object, right? Imagine a mattress. So when mattress has many spring coils, and then when you touch the mattress, let's say this is the finger that's touching the mattress, you deform the shape a little, right? So the springs inside here is now being compressed. If you press it down, what it does on your finger, it's going to give you force back on your finger. So that is similar to the normal force. When you push, when you're in contact with the solid surface, and you're distorting tiny bit, but you're distorting all these tiny little springs a little bit, and these springs is pushing you back as normal force or the support force. And that's why so it comes from the surface, and that's why the direction is always perpendicular to the surface, upward, right? Outward direction. That's what the normal force is. So let's see an example. Simple case. Here is an apple. I learned a technique from my student. Yeah. So here's an apple that's on a rest on a table, let's say. And what are the forces exerting on the apple, right? And if you want to find out the forces exerted on the apple, you draw little dots. This is the object that you're looking at. And then from here, you always have a gravitational force. What's the direction of a gravitational force? Always vertically downward. So let's draw downward. Looks pretty vertically downward. And make sure to label. And I say vertically downward. And this apple is at rest, correct? This apple at rest on the table. So when the apple is at rest, what's the net force on the apple? Net force on the apple has to be equals to 0. That means that what else is the force exerted on the apple? You have a gravitational force vertically downward, and that's right, the normal force, the support force, right? That's going to be, and what is the direction of this normal force? Over here, it says always perpendicular to the surface. So in this case, you're going to draw something like this. Uh-oh, that's not what I meant. Like that. And since that, are there any other forces exerted on the apple? No other forces. So the net force is Fg plus N. And we say because the apple is at rest equals 0. So you know that gravitational force, normal force has to be, in this case, the normal force is negative of Fg. So they're equal in magnitude, right? They're equal in magnitude and opposite in direction. They're canceling out each other. We've done that many times. Now we're going to look at the same apple. It's exact the same apple, but let's tilt the plane that the apple is sitting. So instead of an apple that's being on a flat surface, now apple is on an inclined surface. And to make things easier, I'm going to make sure that says this is no friction. Very slippery. So now another case is that an apple on an inclined plane. Right? When the apple is on the inclined plane, what are the forces exerted on the apple? One obvious one is always gravitational force. What's the direction of the gravitational force? Vertically downward. Does gravitational force has changed from when it's on the flat surface to the incline? Does it change? No, it doesn't change. Gravitational force only depends on its mass, right? So the magnitude of gravitational force hasn't changed, and still it's vertically downward. So I'm going to draw the exact same vector as I did before on the flat surface, correct? Because it's the same apple. So nothing is changed. Just because it's on the plane, inclined plane, it doesn't mean the gravitational force changes. Okay. So this is the same gravitational force on the apple. Should write down. Let me just write that down. So gravitational force, the magnitude of gravitational force only depends on, I shouldn't say only depends on, because we're going to do something else that's not near the surface of the earth, then you might see things different, but depends on near the surface of the earth, depends on its mass and the gravitational acceleration. That's what the magnitude, right? And gravitational force is direction still vertically downward. Downward, sorry. So in this case, it hasn't changed. So this is this is The same, exact same, same. No change. Agree, right? So the gravitational force doesn't change. Just because you tilt the plane, it doesn't mean the gravitational force changes. Are you going to be the gravitational force, if you change the plane, does that, you're going to push down harder? But something different happens. When the apple is on a slippery inclined plane, instead of if it's on a flat surface, is it still at rest? Let me share. So let's see. I want to share this with you. There is a toy on a flat surface in this video right now that's posed. So then I'm going to tilt this. So I'm going to tilt this plane, but before it's being tilted, you see the toy is at rest on the surface. It's not moving, just like the apple example we just did. Then let's see what happens if I tilt the plane now and see what happens to this toy. All I'm doing is just tilting. I'm not pushing or anything. You know what it does. It starts moving. As you see that there is no new forces exerted, correct? Is there any new forces? Just tilt it, slice it, assuming there is no friction. What about when it's moving on the incline? What is the force exerted on this toy? If I let go of my finger, what are the forces exerted on the toy? There is always gravitational force and normal force. What happens if I increase the angle? Okay. What really happens if I do this? And that's going to do if I completely make them vertical. I don't think my sound would like it. You see? So then I'm going to tilt this plane now. All right, so let me see, stop sharing. So you see that as I increase the angle, there's even, if I have an incline, the toy is starting to roll down on an incline, starting to roll down, starting to move. And then if I increase the angle even more, it even rolls down faster. And at the end, when I made it completely vertical, it just, what did it do? Just fell out of it, right? It didn't even slide down. It just went down. Is that right? So let's analyze this. And by doing this way, the only thing that changed is the angle of incline. So starting from 0, completely horizontal, and then I changed the angle, right? And that's all it has happened. There's no new force exerted, is that right? Did I push it? No, there's no push force, nothing else. And we say the gravitational force doesn't change. It shouldn't, same mass, same toy. So something else has to be happening. I'm gonna go to the notebook. Here, I came back, right? So we're gonna analyze this. As we just drawn these arrows, the vector arrows, right? The gravitational force stays the same. Here, to analyze this, we use something that's called vector decomposition. So let's talk about vector decomposition here. Vector decomposition. Vector decomposition is something like this. So you could have a vector here, any vector. Let's say vector A, right? And this vector A is just any random vector. It could be any arbitrary vector. But instead of looking at a vector A as this vector, we can think about this A vector is a resultant of this vector plus this vector. It's the same thing as AX plus AY. We can just say A is equals to, same thing. So you can either just say AX plus AY or A. So what I'm doing here is this A is equals to AX plus AY. AX plus AY. So instead of looking at this one A vector, we can see that AX and AY. So we decompose the vector as AX and AY. Here what we have in a gravitational force on the incline. So apple on the incline, right? And the gravitational force is vertically downward. Let's decompose this into, and so you can decompose the A vector into AX and AY, AX and AY like this, or you can even decompose into perpendicular and parallel. Any vectors you can decompose into as long as you go, just like you might not have done the worksheet, but like you can go from your parking lot to the physics classroom direct, or you can go to the library, bathroom, and then to the physics classroom. Even though you go take the different route, as long as you sum up all those vectors and the initial and final is the same, then it's the same resultant, right? So instead of seeing it as the direct route, it can be the same thing as the sum of library, bathroom, and to the physics classroom. So here in this gravitational force that's always vertically downward, and it's the same as a flat, but now instead of seeing just a flat, we're going to decompose this into some of this gravitational force is made of this. And then plus some of the gravitational force is made of this much. So I'm going to call this as a FG perpendicular to the surface, and I'm going to call this arrow as a FG that's parallel to the surface. So you can see, I hope, is that FG is the same thing as FG parallel plus FG perpendicular. Let's go back and then think about when the apple was on top of the flat surface, right? Oh. When the apple is on top of the flat surface, there was a gravitational force, the same amount. Fg downward. And if I want to decompose this gravitational force into perpendicular and a parallel component, all the gravitational force is actually Fg perpendicular. In this case, the Fg parallel to the surface is 0, right? There's no parallel component. And imagine, remember the normal, what's the direction of a normal force? Direction of normal force is always perpendicular to the surface. So if you push it, if you don't, and also the normal force, if you don't touch the mattress won't push you back. If you touch the mattress lightly, mattress will push you back a little bit lightly. If you push it hard, it pushes you back the harder. The more you push, the bigger it pushes back, right? So whatever that you push, the normal force is the same thing. If you push it hard, perpendicular to the surface, it pushes you back in perpendicular to the surface. So here we have all the gravitational forces pressing the surface perpendicularly. Then the normal force is going to push back on the same amount, push back, same amount, perpendicular to the surface as this, as the same amount as this, and this is the same. So Fg perpendicular and the normal force is the same. However, let's go back to the apple on the incline. When the apple is on an incline, some of the gravitational force is pushing the surface perpendicularly, but now some of the gravitational force is actually pushing down along the surface. By decomposing the vector, you can see. So then, the normal force in this case, how much the surface is pushing back this apple, how much the surface is going to push back the apple will be a little bit less than before, like maybe this much. Because the gravitational force that's pushing this apple perpendicular to the surface is now, how did it change? Did it stay the same or decrease or increased? This gravitational force and this gravitational force. From moving it to the incline, if you change to an incline, did it increase? Stay the same? Decreased, right? As an incline. Because the FG parallel, and then instead the FG parallel, before it was 0, now there's a FG parallel that's non-zero. So the normal force now is this normal force as you moved from the flat surface to the inclined plane also decreased. And it's this normal force and then FG perpendicular, that's equal and opposite to each other. So instead, what is the net force on the apple on the incline? Net force on the apple on the flat surface, which is Fg plus N, that was equals to 0 before. Now, net force on the apple, it's still just the gravitational force plus the normal force. But instead of seeing the gravitational force as a whole thing, you're going to say Fg perpendicular plus n. And I say these two cancels out. So net force on the apple on the incline will be just this. So it's no longer not zero. Because the normal force now decreases. So let's see, right? Normal force decreases. So this is decreased. As incline. Then, but let me see. But this stays same. Gravitational force stay the same. Normal force decreases as the inclined plane increase because of the perpendicular component of the gravitational force decreases. So what happens if so you see it like this, okay? Right, flat to this, normal force decreases because the perpendicular component of the gravitational force decreases. And now we have a parallel component of the gravitational force increase as the incline is getting steeper and steeper. So I'm going to do another case. Let's increase the incline of the apple, where the apple is sitting on. The gravitational force, what happens to the gravitational force? Stays the same, increase, decrease. Gravitational force stays the same. But when you decompose the gravitational force, now maybe this is perpendicular to the surface. So I want you to draw this on your note. That I want you to practice decomposing the vectors, gravitational force vectors, into perpendicular and the parallel. Okay, then let's draw the normal force. So the normal force now is going to be equal and opposite to the Fg perpendicular component. So it's going to be this much. See? Same as this much. That's equal and opposite. You can see the apple won't jump out from the plane or break the plane. So there's no motion that's perpendicular to the plane. The only motion that it's left over is this part. This is going to be the left out. So again, the net force on this case, net force, is still only we have a gravitational force and a normal force. That hasn't changed. And then instead of seeing gravitational force as the one entire gravitational force, I can decompose into parallel plus Fg perpendicular plus n, and then Fg perpendicular and n, normal force cancels out. So what's left is going to be net force is Fg, parallel. That's the net force. So sliding down, that's why sliding down. Along the plane. This one too slides down. the plane. Right? But what happens when I increase the angle even steeper, as you saw on that demo? These FG components, as you make the angle steeper and steeper, sorry. So what you see as an incline angle increase. If you have a steeper and steeper incline, then this FG parallel, what happens to the parallel component of that FG? FG, before that, let me just do this, sorry. What happens to the gravitational force? Gravitational force stays the same. What happens to the FG perpendicular as the angle increases? Decrease, increase, stay the same? Decreases. Therefore, and then what happens to the normal force? Normal force increases, stays the same, decreases. Normal force decreases. And what happened to the FG parallel component? Increases. Right? So as the angle of the incline increases, FG, the gravitational force itself don't change, but it doesn't push the surface as much, so therefore normal force decreases. So left over, the net force, the gravitational force parallel increases. That's why it goes faster and faster. And then when I make it completely vertical, when it's completely vertical, what happens to the apple? What happens to the gravitational force of the apple? Stays the same. So still, you have it like this. Gravitational force always vertically downward in the same amount. It only depends on the mass. And then if you want to decompose it, you can see that entire gravitational force is going to be parallel component. Now, FG perpendicular is equals to 0. Therefore, what happens to the normal force? Normal force is also 0. So that's what you saw on the demonstration that I can show you again. Let's see. I'm going to show you again. See what happens to this toy. All I'm doing is just tilting. I'm not pushing or anything. You know what it does. It starts moving. As you see that there is no new forces exerted, correct? Is there any new forces? Just tilt it, slice it, assuming there is no friction. What about when it's moving on the incline? What is the force exerted on this toy? If I let go of my finger, what are the forces exerted on the toy? There is always gravitational force and normal force. What happens if I increase the angle? Okay. What really happens if I do this? And that's gonna do if I completely become vertical. I don't think my sound would like it. You see? So you see that see again on the demonstration, right? Um, here. Um, when you step on the scale, scale, how does the scale measure your weight? Before that, let me see. Before I talk about the scale, let me just finish up. So when the wall is completely vertical, as you see, the entire gravitational force is parallel. So what's the net force? What's the net force? Net force is gravitational force. So all we do is by changing the angle of incline, the normal force changes to be less and less as the increasing angle. And that's why it changes the motion. It's not that you're adding a new force. Actually, you're taking now the normal force. When you go to a physical exam, you step on a scale to measure your weight. Inside this scale, there are a bunch of spring coils, and they feel the force you're pushing up, down. So on you, you have, what do you have? You always have a gravitational force, right? Direction of a gravitational force is vertically downward. So this is the FG that's pointing vertically downward. And you also have a scale pushing you up, right? So you push down the scale is going to push you up perpendicular to the surface. And that is it's the response force from the scale. So that is the normal force, that scale. So this normal force comes from, that's what scale reads. It's the response force from the scale is what's measuring your weight. So when you put the scale on the incline, now you're on the incline. What is going to be the gravitational force? Gravitational force stays the same. How does the scale read? Is it increases? Does your weight, what happens to your weight? Increase? What happens to your weight? Does it increases, decreases, stays the same? You know gravitational force doesn't change. What happens to your weight when you're on an incline? In fact, what happens? What happens? Ah, it's this way. What happens to your weight when you're completely vertical? What does gravitational force is always vertically downward. your weight. When you're completely vertical to the wall, does it change? Okay, so this is going to be the end of this video. It was a little bit long, but yeah, I want you to make sure to review it and then understand the vector decomposition and the normal force. And what scale reads is the normal force, not the gravitational force.